Welcome back. So, we have discussed in the last class steel electron beam welding technique. So, this class we will start with plasma arc welding, which is another advanced welding technique. So, what is the principle of plasma arc welding? So, it is a constricted arc process. So, the arc is constrained with the help of a water cooled small diameter nozzle, which squeezes the arc, increases its pressure, temperature and heat intensely, and thus improves stability, arc shape and heat transfer characteristics. So, there are two methods of plasma arc welding, that is transferred arc and non-transferred arc. So, what are the differences between them? So, when the electrode, you can see this is basically the negative electrode, that is cathode, and this is the workpiece, that is anode, that is the positive electrode. So, when it is the connection is made with the negative electrode and positive electrode, then we call it as transferred arc plasma welding technique, plasma arc welding. And when the connection is circuit is terminated with the nozzle end, the positive workpiece is connected with the positive polarity is connected with the nozzle end from where the arc is generated. So, then we call it as non-transferred arc. So, in case of transferred arc, the electrical circuit is between like tungsten electrode and the workpiece. So, the workpiece acts as anode and the electrode as cathode. So, the arc is transferred from the electrode to the workpiece and hence the term transferred. So, here the arc force is directed away from the plasma torch and into the workpiece, hence capable of heating the workpiece to a much higher temperature, and which is you can understand here. So, that is why the weld pool is created by the arc generated by the plasma, and it is also capable of producing intense localized heat. So, that is why you can see the weld pool reaches the throughout the thickness of the workpieces, and that is why you can see this is again an example of a single V bar joint, where a single V is enough for the almost to a greater thickness of the workpiece material. So, because of the higher localized heating capability of the plasma arc. So, in case of non-transferred arc, the power is directly connected with the electrode and the torch of the nozzle. So, the electrode carries the same current, thus ionizing a high velocity gas that is strewing towards the workpiece. The main advantage of this type is that the spot moves inside the wall and heat the incoming gas and outer layer remains cool. So, this type of plasma has low thermal efficiency. So, again, although it is it is, you can say that it is easier to handle in this way. So, because the circuit ends in here. So, here this is in case of non-transferred arc. So, non-transferred arc, but however, and that is easier to handle in a way that it can keep the it can increase the longevity of the plasma arc welding nozzle, also keep the temperature of the body much cooler. However, it is not efficient enough to heat the joint compared to the transferred arc plasma arc welding route. So, that is why it is the transfer arc technique is more preferred. So, the advantages, it ensures arc stability, the plasma arc welding technique as a whole. It produces lesser thermal distortion compared to arc welding or gas welding techniques. The process is readily automated. However, the disadvantages are excessive noise, complicated and costly equipment, and large amount of ultraviolet and infrared rays emission in case of plasma arc welding technique. So, then we are moving to a much widely used variant of arc welding, that is called metal inert gas welding. So, you can see here this is basically one of the basic systems. So, the arc welding, the arc generation principle is pretty same that we have discussed earlier when we have discussed about the principle at the start of the welding section of the course. So, that is why I am not repeating that. So, here we are focusing about the process alone. So, here we are dealing with a consumable electrode, and also there is a gas shielding that is kept over the joint to prevent the chances of oxidation and also gas absorption. If it is a light metal, then there is a high chances of hydrogen absorption in the joint, which can cause big porosity, and which can then also weaken the structural integrity of the joint, and which can cause failure while subjecting it to the service. So, so what is the circuitry involved here? The equipment involves a welding gun, a shielding gas, protective environment, and the arc which is generated at the tip of the electrode, and there is a wire feeder, because generally in case of MIG welding we do not use rod type electrode, only for educational purpose we can use, but otherwise for industrial parlances it is the wire type electrode, which is a consumable electrode which is fed using appropriate spool to the weld zone. So, this is how it is used. So, it can all work with both AC and DC power supply. Okay. And so the working is it to be, so it is the pretty same as we have discussed the arc welding principle. So, so here the electrode is brought near the workpiece with a small air gap and the arc is produced. So, this arc melts the electrode, the melted electrode fills uniformly over the required regions of the workpiece for joint formation, and inert gas supply is provided around the electrode, and hence the name metal inert gas welding is given. So, during the welding process, so it forms a gas shield to prevent oxidation and gas entrapment in the joint. So, the type of electrode used and the shielding gas used primarily depends on the material to be welded. So, it is the workpiece material that serves as a deciding factor on the choice of the electrode material and on the choice of the protective shielding gas. So, it needs to be ensured that the gas does not react with the workpiece either in solid form or with the weld pool generated at the adjoining faying surfaces. So, in many cases the shielding gas used is a mixture of many gases, mostly these are inert gases such as argon, nitrogen, etc. So, if many workpieces are to be welded continuously, an electrode spool in the form of coil is used, as I told you that it is the technique which is followed in industrial parlances, and nowadays also there is a improvement evolution of the metal inert gas welding to develop the wire arc additive manufacturing technique, that we will be discussing briefly when we will go into the additive manufacturing section of this course. So, this is for your knowledge. So, in MIG welding consumable electrode itself acts as a filler metal. So, no separate filler rod or filler wire is needed, and which is used in case of tungsten inert gas welding, that we will be discussing next. So, the advantages of MIG are consumable electrodes are easy to feed, simple welding, no filler rod is needed, and inert gas shield protects the weld automatically. And the disadvantages are improper welding may lead to the floating of solid impurities over the liquid weld. If it is not handled properly, weld can become porous, like if the shielding gas is not capable or shielding gas is not applied, or its thickness of the gas layer is not enough, it can cause severe gas absorption and porosity formation within the joint. And MIG welding exposes welders to hazardous gases. Care must be taken to avoid the formation of less ductile welds. So, workpieces and electrodes should be kept clean before welding, because otherwise it can cause inclusion entrapment in the weld joint region. Okay. So, now we will move into the tungsten inert gas welding. So, the working principle is pretty similar with the metal inert gas welding technique. Only difference is that in this case we use non-consumable tungsten electrode for arc generation, and other things are same, like electrode serves as a negative polarity, and the workpiece serves as anode with a positive polarity. And so, the filler metal so it can be both. So, TIG can also be autogenous, that means where there is no need for filler material. So, that only work for smaller joint development, whereas there is whenever there is joint thickness is significant, then we need to use externally added filler material. So, that is what is shown over here, the filler rod. So, it can also be fed in the form of a wire using a spool to the welding zone, just beneath the welding torch where the arc is produced. So, in that case it can be either homogeneous or heterogeneous, that means with filler metal assisted technique. Okay. So this is the basics of TIG welding technique. So it is a widely employed technique because of its capability to achieve precision joining of critical components, which requires controlled heat input. The small intense heat source provided by the tungsten arc is ideally suited to the controlled melting of the material, since the electrode is not consumed during this process. As such, in case of MIG technique, welding without filler material can be done without the need for continual compromise between the heat input from the arc and the melting of the filler metal. So, the situations where autogenous welding serves the fits the bill, then it is always recommended to go for TIG rather than MIG. Okay. So, so in this case, so TIG electrode selection is a key. So, generally, although we are calling it as a non-consumable electrode, however, there is some amount of vaporization and losses happens to the electrode with continual usage, and also electrode composition and size is not completely independent and must be considered in relation to the operating mode and the current level. So, electrodes for DC welding are pure tungsten or tungsten with 1 or 2% thoria. So, the thoria being added to improve electron emission, which facilitates easy arc ignition. Which is otherwise to avoid any time delay. So, that is why the thoria coating is generally employed over tungsten electrode. In AC welding, where the electrode must operate at a higher temperature, a pure tungsten or tungsten zirconia electrode is preferred, as the rate of tungsten loss is somewhat lesser than with thoriated electrodes, and the zirconia aids retention of the ball tip. So, ball tip means it is the tip of the electrode. So, this is basically we call it as ball tip. So, this facilitates accurate arc length monitoring. Arc length keeping the arc length intact or accurate, so that effective welding, effective heat input in a localized manner to the joint can be achieved. So, in case of DC welding, we use thoriated tungsten electrode, and in case of AC welding, we used tungsten electrode either in pure form or alloyed with zirconia. So, this is what and the power, so the power source is similar to like we have discussed earlier. So, we use a drooping characteristics for drooping current characteristics for TIG welding as well. So, as we discussed earlier, drooping current characteristics ensures the change in arc length does not cause much change in the welding current. So, that we can ensure continuous welding process with a consistent efficiency and a with a consistent heat input and melting rate for joint preparation. So, the capacity to limit the current to the set value is equally crucial when the electrode is short circuited to the workpiece. Otherwise, excessively high current shall flow, damaging the electrode. So, the open circuit voltage of power source ranges from 60 to 80 volt. So, that we have talked before, and the applications are, so pure argon can be used for welding of structural steels, low alloyed steels, stainless steels, aluminum, copper, etc. So, all these metals can be joined by tungsten inert gas welding. Argon hydrogen mixture is used for welding of some grades of stainless steels and nickel alloys, and also pure helium can be used for aluminum and copper, and helium argon mixtures may be used for low alloy steels, aluminum and copper. So, TIG welding can be used in all positions. It is normally used for root passes during welding of thick plates, thick pipes, because but is widely being used for welding of thin walled pipes and tubes. So, so these are the applicability of the TIG welding technique. So, you can understand that it is widely utilized technique across various industries. So, this process can be easily mechanized, that is movement of torch and feeding of filler wire. So, it can be used for precision welding in nuclear, aircraft, chemical, automotive and spacecraft industries. So, so aircraft frames and its skin, rocket body, engine casing are few critical examples where TIG welding is very popular. So now moving ahead, we reach the forge welding. So this is a typical example of solid state welding technique, where we are, I mean, this forge welding is one of the primitive and the basic solid state welding technique. So in this case, a charcoal forge, I mean, the is used to heat up the workpiece material, I mean, to adjoining, I mean, faying surfaces. So these are called faying surfaces of these two adjoining cylindrical metal rods. So they are basically heated by charcoal, and then I mean, so the blacksmith heated the, after heating the workpieces to be welded to a practical forging temperature, and then end preparation is done by hammering, so that they could be properly fitted together. The ends were then reheated and dipped into a borax flux. So heating was continued until the blacksmith judges by color that the workpieces were at a proper temperature for welding. They were then withdrawn from the heat and either stuck on the anvil or hit by hammer to remove any loose scale or impurities. So this is the, I mean, initial step of joint preparation or preparation of the faying surface, because if the faying surfaces are not made clean from the oxides or the scales, then the joint property will be inferior, and there will be every possibility for failure of the joint from the locations where there is entrapment of oxide skin or scale, loose scale. So the ends to be joined were then overlapped on the anvil and hammered to the degree necessary to produce an acceptable weld. So this is the philosophy of forge welding, and the applications are that it is used to join steel or iron, it is used to manufacture gates, prison cells, etc. It is widely used in cookware. It is used to join boiler plates before introduction of other welding processes, and it is also used to weld weapons like sword, etc. and I mean, also shotgun barrels. So these are because it is a technique which is there since ages, and it is also used for, I mean, several, I mean, applications which we did generally see in our day to day usage. And the advantages are quite self explanatory, that is, it is a simple and easy technique and does not need any special equipment, but however it needs a I mean, operator skill, and so that is also a major disadvantage. And so although I mean it can it can be utilized to weld both similar as well as dissimilar melts, and without needing to use any filler material. And moreover, the properties of the joint is very much similar to the base material, because here we are not dealing with the melting of the adjoining region or the joint region. So there is no weld metal produced. So that is why there is, I mean, very little differences in the microstructural attributes in the base metal and also in the joint. So that is why the variation in mechanical properties is also much lesser. So the disadvantages are, I mean, small objects can only be welded by the larger objects requires large press and heating furnaces, so which is not economical. And operator skill dependence is also a major concern, and it I mean, high welding defects are possible in this technique, and it is a slow welding process, and that is why not I mean, being practiced in industrial parlance. So I mean, the next in the list is cold welding. So it is a variation of forge welding that uses no heating but produces metallurgical bonds by means of room temperature plastic deformation. So the surfaces to be joined are first cleaned and placed in contact, and then they are subjected to high localized pressure sufficient to cause about 30 to 50% cold work. So while some heating will occur due to the severe deformation, the primary factor in producing coalescence is the high pressure acting on the newly formed surface material. So the cold working process is generally confined to the joining of small parts made from soft ductile metal, such as the electrical connections as shown over here. So these are the examples of the, I mean, cold welding technique. And then roll welding. So roll welding, so this is a technique, it is called, I mean, roll bonding as well, which is abbreviated as ROW. So here two or more sheets or plates of metal are joined by passing them simultaneously through a rolling mill. So, in this case it is a typical example of two high rolling mill, where you can see both the rollers are basically rotating in the counterclockwise direction. So the upper roller is basically rotating in the counterclockwise direction and the bottom roller is rotating in the clockwise direction, and that is why they are allowing the plates or parts to be welded to pass through them, and that time they exert compressive load over the plates, and which are having fairing surfaces, and because of the compressive load the joint is formed at the region of contact. So, as the materials are reduced in thickness, the length and or width must increase, so to compensate. The newly created uncontaminated interfaces are pressed together by the rolls and coalescence is produced. So, roll bonding can be performed either at a hot or cold state and can be used to join either similar or dissimilar metals such as aluminum's a skin of high corrosion resistance aluminum over a core of high strength aluminum, or conventional steel with a stainless steel cladding. So, this is a typical technique which is mostly driven by plastic flow of matter and associated atomistic bonding forms between the adjoining layers of the sheets which are experiencing joining to each other, and so this is also a technique of cladding. So, although nowadays there are advanced cladding techniques such as laser cladding techniques which has been evolved and which are very much useful to make claddings with much reduced thicknesses. However, this is a technique where a significant thickness of the cladding layer is needed there, and also the it is when we are talking about sheet metals or thin sections. So, there it is more economical to do it by this roll welding route. So, a common example of this technique is in the manufacturing of refrigerator freezer panels. So, like those where inexpensive sheet metal is used to produce structural panels can also be utilized by can also be achieve the cladding via roll welding route. And so, then we will move into the friction welding. So, you can understand the working principle from the schematic itself. So, in step 1 you can see that there is a so it is what is the primary constraints of the friction welding route, that we can only weld cylindrical rods, cylindrical objects by friction welding technique. So, in this case, so one one workpiece is non-rotating and clamped firmly, and the other one is rotating, and then while rotating it is basically kept in touch with the non-rotating workpiece. So, then when it is kept in contact with the non-rotating workpiece, there is significant friction generated at the interface, at the fairing surface, and then in step 3 so the pressure is applied. So, because in step 2 the pressure applied is only that much, which is ensures contact between the rotating and non-rotating parts, and because of that the friction generated, and that is why the softening happens at the fairing surfaces. And then in the step 4 when basically we are in the after step 2 when we are moving into the step 3. So, in that case the pressure is basically increased. So, so because of the increase of the pressure there is some plastic deformation takes place at the fairing surfaces between the rotating and the non-rotating workpiece, and that is why the hump is created that you can see over here. So, because of the plastic flow of the matter, and it is the initiation of the welding that happens, friction welding that happens at the adjoining region. And in step 4 when we move to the step 4, then suddenly the rotating member rotation has it generally stops, and then the pressure applied increases, and that is why the offset welding takes place at the adjoining fairing surfaces, and this is the hump generated which can be trimmed off post welding. So, there are many types of friction welding processes which works differently, but all different these processes involve common working principle, that is what I have explained to you. So, this is how we basically achieve. It is a very clean welds can be produced, because we are not talking about producing liquid melt, we are not talking about any filler material addition or any gas cover. So, that is why it is a purely solid state welding technique. So, mechanization of the friction welding technique can be termed as continuous friction welding. So, that is you can, what is mechanized over here. So, the mechanization involves, so this welding is same as we have discussed in case of friction welding. So, in this welding technique, the rotor is connected with a band brake. So, when the friction crosses the limit of plastic temperature, the band brake comes into action, which stops the rotor, but the pressure applied on the workpiece increasingly until the weld is formed. So, only difference with the friction welding technique is that in case of continuous friction welding, the manual intervention of monitoring the plastification of the adjoining faying surfaces of both the cylindrical workpieces, which are going to get joined to each other, in spite of manual intervention, that the brake which is kept, that is the band brake, basically stops the rotation of the rotating member of the workpiece, and then the pressure increases, and that is why we basically achieve a cleaner friction welded joint at the adjoining region. Okay. So, the advantages of continuous friction welding are, it is useful for welding tubes and shafts. It is mostly used in aerospace, automotive, marine and oil industries, and also in gears, axle tubes, valves, etc. And there are several other applications, in electrical industries also, for copper aluminum equipments, also in pumps, gear levers, drill bits, etc. So, the advantages are, it is environment friendly, as I already mentioned, that there is no need for any protecting gas shield, or any no heat generation or smoke generation is involved. Heat generation is there, but that is not up to the level of weld pool formation, as we have discussed in case of friction welding, or in case of arc welding, or in case of gas welding, and also in case of laser and electron beam assisted welding. So, here a narrow heat affected zone forms. So, no change in properties of heat sensitive material, no filler metal is required, welding strength is strong in most cases, because we are plastically deforming the material at the adjoining region. So, so you can very well understand that the weld joint will be stronger than the joint we generally produce by fusion welding route. So, so the process is easily atomizable. Automated automation is possible quite effectively, and it also deals with high welding speed, high efficiency of the weld, and wide variety of metals can be welded. Even dissimilar metals can be welded effectively by friction welding route. Of course, there has to be molecular bonding need to take place. So, that compatibility must be there, but otherwise it can be utilized for welding dissimilar metals. And the disadvantages, as I told earlier, that it is the shape limitation of the workpieces that can be welded. So, it is mostly useful for round bars of similar cross section, and so it demands for a preparation of workpiece much more than the other welding technique, and that increases the cost of the recurring cost of the welding technique, and also it deals with a high setup cost, and the joint design is limited. So, so these are the disadvantages of the continuous friction welding technique. So, then we move to the friction stir welding technique, which is the one of the most advanced welding technique. It is again a solid state welding technique. So, in this case, a non consumable rotating tool with a specially designed pin and shoulder is inserted into the abutting edges of sheets or plates to be joined and traversed along the line of the joint. So, the tool serves two primary functions. So, this is basically the tool, rotating tool, that we generally used in case of friction stir welding. So, this is the FSW tool. So, this is the pin section, this is the shoulder section that is marked over here. So, the pin sections goes inside the workpiece, and which is responsible for rotating inside the workpiece for joint preparation. So, it the tool serves the heating the workpiece by frictional heating, and then number 2, it serves as the movement of material to produce the joint. So, the heating is accomplished by friction between the tool and the workpiece and plastic deformation of the workpiece. So, the localized heating softens the material around the pin, and the combination of tool rotation and translation. So, here it is like the tool which is getting inserted into the workpiece, which is responsible for plastifying the material and also movement of the material across the length of the weld. So, it is only possible because of the combination of tool rotation and also its translation, which leads to the material movement from the front of the pin to the back of the pin. So, this is how we can achieve, and here depending upon the joint architecture and also the material involved, we can we can achieve the joint in case of friction stir welding with a variety of pins and solder design. So, we can use threaded pin, we can use threaded pin with flutes. So, this depends on the degree of friction needed and the degree of joint design and the amount of matter, the metal that needs to be that needs to be plasticized. And so, here it is a technique, it is again a autogenous welding technique, where the material and the metal which is drawn into the joint from the parent workpieces itself. And so, it is again it is not melting, it does not deal with melting of the matter involved for joint preparation, rather it deals with the plasticizing of the material. And so, the metallurgical benefits of friction stir welding is its excellent weld quality, applicable to a wide range of materials including some non-weldable by fusion methods. It is a solid state technique. So, it deals with low distortion of the workpiece, because only heating takes place because of the friction and in a highly localized manner. So, the distortion of the assembly, the weld joint assembly is much lesser, and it is possible to achieve very high joint strength, no loss of alloying elements, fine microstructure because of the significant plasticizing of the metal at the joints region, and that is why fine grain microstructure we can achieve, and no cracking is involved because there is no phase transformation involved in this case. So, that is why the difficulties with that, like hot cracking and all. So, these difficulties are nullified, and the environmental benefits, because here there is no shielding gases are needed, no filler material is needed. So, no solvent degassing is used, or fumes or smokes are not produced. So, it is very much sustainable technique and environmentally benign technique, and that is also a primary reason. That is why it is being it is largely replacing the electroslag welding technique for for welds having deeper vertical welds having deeper depth, so because of its sustainable nature. And the energy benefits are the welds produced with far less energy than in other processes, and it enables weight reduction in aircraft, automotives and ships. So, it is because mostly suitable to the light metals, and we know that the difficulty associated with the casting as well as fusion welding of light metals such as aluminum, magnesium, because of their tendency and their towards gas absorption, which can cause significant defects in the weld joint and significantly decrease its mechanical property. So, all those all those troubles can be completely nullified by resorting to this solid state welding technique called friction stir welding. Okay. So, with this we are stopping for this class, and in the next class we will discuss about some other welding techniques, and also about the different defects that generally forms during fusion welding, and also we will discuss the different techniques, destructive and non-destructive routes that techniques that we follow for estimating the quality of the weld joint before subjecting the weld assembly which is experiencing weld joint to its intended service. So, till then, thank you. So we will meet in the next class.